Hi, my name is Justine Harkness, and in this video, we'll look at how to apply Kirchhoff's rules to calculate currents when we have multiple batteries in a circuit. The first step in solving these problems is to determine our loops. So say we have this example circuit. We have two batteries and we have one resistor. The first thing we need to do is label the currents on our diagram. A great place to start is to have our currents coming from the positive terminal of our battery. So we can label the currents coming from our terminals. These currents are going to come together at the node to form one larger current, and that current will split on the other node. So we can label these as I1. We have I2 on the other side, and we'd have I3 going down. Now we have to draw a complete loop, and this must always follow the direction of the current. We'll look at two different loops. So the first loop we're going to draw will be coming from our positive terminal of the battery. Notice we are going in the same direction as the current. Come down that node and come back. So at every point in this loop, we are going in the same direction of the current, so this would be a valid loop. Now if we look at a bad example of a loop, we could start at that same point and then go around the entire thing. Notice that in this loop, on the right-hand side, we are going in the opposite direction of our current. So this would be not a valid loop. So not be valid. Now, once we have our loops established, we need to set up our loop equations. And we have to be very careful with the sign designations. Now remember, Kirchhoff's loop rule says that our voltage drop in any complete loop will be 0. Now as we think about our signs, we have to consider what happens as we go through a battery. So here we have a battery. I have a negative and a positive terminal. If I go from the negative to the positive terminal, I will gain voltage. So the sign of voltage there would be positive. However, if I go from the positive terminal to the negative terminal of the battery, I will lose voltage, so the sign of my voltage will be negative. In terms of resistors, though, anytime we go through a resistor, the voltage drop is always negative. The final thing we need to do is to set the current into a node equal to the current out of a node. This is our node rule. What you should be left with are a system of equations where you should have the same number of equations as you do variables. So you just need to solve these equations algebraically. So let's take a look at an example and work through all of our steps. So this question gives us a circuit diagram and asks us to calculate the currents and their direction for this circuit. So the first thing we need to do is to set up our currents, and we can start with this 20-volt battery. So we're going to have a current leaving this battery, which will go around through that 100-ohm resistor, and we can label this as I1. Now notice there's another battery on the other side. We'll just, not worry about this one for now, but there will be a node here. So there'll be a combination of currents, so we can label this as I3 for now. And this current will come down and then split. So we have I3 and we have I1, which will then come back to our battery. On the right-hand side, we have a 30-volt battery. We'll have our current leaving here, which will be I2. This will come into our node. This will be I2. And of course, it has to come back to the battery as well, so that means we have to label I2 on the top here, returning to our battery. Now at this point, it doesn't really matter which direction you put your currents as long as you're consistent at your nodes. If you find that one of the currents should actually be pointing the opposite direction, you'll know that once you start solving your equations. If the current that you get is negative, that means that your original designation was pointing in the opposite direction, and in that case, you would just flip your arrow. Now we have to determine our loops. So we can start at this 20-volt battery. We'll go around. We go through that 100 ohm resistor. We go through that 75 ohm resistor. And we come back to our original position. Now notice we're going up this battery. We're going from the negative side to the positive side. So we're going to gain voltage. So our voltage here would be positive. Now we are going across this 100 ohm resistor. Anytime you go through a resistor, the voltage drop will always be negative. And if we look at the voltage drop across this resistor, it would be the current, I1, times our resistance, which would be 100 ohms. So this would be minus 100 I1. And then we're going through that 75 ohm resistor. Notice that the current here is I3. So this would be minus 75 I3. And this brings us back to the battery. So it's a complete loop. So the voltage drop here across this entire loop has to equal 0. Now, if we were to try to do that same loop on the other side, notice we would be starting here, going around, but we'd have to go in the opposite direction as I3. So this would not be a valid loop, so we could not use that. So let's just get rid of it. We have to draw our second loop. So we're going to start at our 20-volt battery. We're going to go around following the current. So this will be essentially the entire thing. So notice again, we are going from the negative to the positive terminal of that 20-volt battery. So it's going to be a positive voltage. Our current I1 goes through this 100 ohm resistor. So we lose voltage. So minus 100 I1. And then we get to that 30-volt battery. We go from the negative to the positive terminal. So we are gaining voltage. So this would be plus 30 volts. And then we have current I2 going through that 200 ohm resistor. So we're going to lose voltage. So minus 200 I2. And this is also going to equal 0. The last thing we need to do is apply our node rule. So we have current 1 coming into this node. So I1. And notice that I2 and I3 are coming out. That means that I1 has to be equal to the sum of I2 and I3. So at this point, we have 3 variables. Variables being I1, I2, and I3. And we also have 3 equations. So at this point, we are set up to solve. So now just comes some algebra. So let's solve our system of equations. We have our equations here in the lower right-hand corner for reference. And to solve for all 3 of our currents, we're going to have to go through a few steps. Now, the first thing that we notice is we already have I1 solved for in terms of I2 and I3. So we're going to substitute in I2 and I3 for I1 in our 2 loop equations. And if we go through and then distribute these hundreds through, we get these 2 equations. Now, one thing that we notice is we have 100 I2 and 300 I2. So if we multiply this equation through by 3 and then subtract them, we're left with one equation that only has one variable, has I3. So we can solve this one pretty quickly. And we get I3 is equal to 0.024 amps. Now we can start substituting in I3 into our other equations. So what we've done here is we've taken our I3 and plugged it back into this equation here. Now what we're going to do is solve. Now we have one equation with one variable. We get I2 as 0.16 amps. Notice that we've solved for I2 and I3. We can go back to our original node equation and plug in I2 and I3 to solve for I1. Notice all of our values for our currents here are positive. This tells us that our original designations for the directions were correct. So we can come back to our figure. We know that I1, I2, and I3 are pointing in the same direction as we have originally designated, and we can go and just label these values. So for I1, we calculated 0.184 amps. For I2, we calculated 0.16 amps. And for I3, that was 0.024 amps. So we got our magnitudes of our currents. We have the direction of our currents. So at this point, we're done. So now you should feel more comfortable using both of Kirchhoff's laws to solve circuits where we have multiple batteries.